Welcome to our deep dive today. We're going beyond just making diffusion models bigger. You already know these models are dominating image, audio, and video generation. But what if there were a way to squeeze even more performance out of them without just adding more layers?
It's all about taking advantage of a unique aspect of diffusion models. Unlike other generative models, they let us strategically allocate compute resources during the generation process, thanks to those denoising steps. But simply cranking up the number of denoising steps only gets us so far.
So we're hitting a ceiling, and we need a different approach. This idea of searching for better noises during diffusion sampling, how did researchers even stumble upon that concept? It sounds kind of backwards.
It might seem counterintuitive, but think of it this way. Diffusion models use random noise as a starting point for crafting images. This research explores whether some starting noises are actually better suited for generating high-quality images, kind of like choosing the right seed for a prize-winning flower.
Okay, so instead of just accepting any random noise, we're being more selective. You mentioned we'll be looking at verifiers and algorithms. What exactly are those in this context?
Think of verifiers as the judges of our generated images. They provide feedback on how well an image matches the desired outcome. Algorithms, on the other hand, are the tools we use to find those better noises, based on the feedback from the verifiers.
And these techniques were tested on ImageNet, Drawbench, and T2I CompBench, some pretty serious image generation benchmarks. So tell me, what's the big takeaway about the potential of this noise search?
The researchers started with a thought experiment, using something called oracle verifiers. Imagine we had these perfect judges who could tell us exactly how the final image would be scored, based on established metrics like FID and IS, which measure image quality and diversity.
So we're pretending we have a crystal ball to tell us which images will be masterpieces.
Exactly. And here's where it gets interesting. Even if we just randomly generated a bunch of samples and let these oracle verifiers pick the best one, we'd see a huge jump in performance. That highlights just how much untapped potential there is in selecting the right starting noise.
So you're telling me that the choice of starting noise has a much bigger impact than we initially thought? That's fascinating because it seems like we've been leaving a lot of performance on the table by not being more deliberate about our starting point.
Absolutely. But of course, in the real world, we don't have these magical oracle verifiers to guide us. So how do we judge the quality of these AI-generated images in a practical way?
Right. We need something a bit more grounded than a crystal ball. What are the options in real-world scenarios?
That's where supervised verifiers come in. These are pre-trained models like CLP and Dino. They're already really good at understanding the connection between images and text, and they can be used to guide our noise search. Essentially, they help us pick noises that lead to images that closely match the class label or text prompt we give them.
So if we want to generate a picture of, say, a cat wearing a hat, these verifiers would make sure we actually get a cat in a hat, and not something totally random.
Precisely. They help ensure that the generated images are aligned with what we're aiming for. What's even more interesting is that the researchers found we can use CLIP, E, and Dino as self-supervised verifiers. Even without specific class labels, they can measure the similarity between the predicted noisy image and the final clean image, and use that as a guide. It's like they've developed their own sense of aesthetics.
That's pretty impressive. They're learning to recognize quality even without us explicitly telling them what to look for. But let's move beyond just picking noises randomly. How do these search algorithms help us find those better noises more efficiently?
Well, there's zero-order search, which iteratively refines the noise based on feedback from the verifier. It doesn't need complex gradient calculations, just feedback on whether a change is better or worse.
So it's a bit like a sculptor slowly refining a piece of art, constantly making small adjustments based on what looks best.
That's a great way to put it. Another algorithm is search over paths, which explores different noise additions along the entire denoising process. Instead of just focusing on the starting point, it looks at the whole journey of generating the image.
So the idea is to find the best sequence of noise adjustments that lead to a high-quality final image. That makes a lot of sense. But I'm curious, what kinds of problems do these algorithms help overcome that we might see with just picking noises randomly?
One issue is mode collapse,
Mm.
where the model gets stuck generating very similar images over and over. These more sophisticated algorithms help introduce more variety and creativity into the process.
It's like giving the model a broader palette to work with. All of this is incredibly impressive, but I know text-to-image generation can be even trickier. What are some of the nuances we encounter when working with larger models in that domain?
We're talking about much larger models,
Yeah.
and the images they create are judged not only on technical aspects, but also on their aesthetic qualities, how well they align with the text prompt, and even their emotional impact.
It's like we've gone from judging technical proficiency to assessing artistic merit. What kind of verifiers can handle such a nuanced task?
We need more specialized verifiers, like aesthetic score predictor, CLIP score, and image reward. These are designed to capture elements that appeal to human preferences, going beyond just objective measures.
So instead of simply checking for accuracy, these verifiers are considering things like composition, style, and even the emotional response the image evokes.
Exactly. And the researchers even experimented with combining multiple verifiers into a verifier ensemble. Think of it like having a panel of art critics, each with their own area of expertise, coming together to provide a well-rounded assessment.
That's a fascinating idea. It seems like we're getting closer to replicating the human process of art critique with these ensembles. But didn't the researchers take this a step further? I remember something about using a language model as a verifier.
Yes, they introduced a fascinating concept called the LLM grader. This involves prompting a large language model to evaluate the generated images based on a set of criteria like accuracy, originality, visual quality, consistency, and even emotional resonance.
Hold on. We're now using AI to judge the artistic merit of other AI-generated images. That's incredible. It seems like we're blurring the lines between human creativity and artificial intelligence. But this brings up an important question. If we have all these different verifiers, how do we know which one is the best fit for a particular task? It seems like there couldn't possibly be a one-size-fits-all solution.
You're absolutely right. There's no single best verifier. The choice depends heavily on the specific task and the data set we're working with.
So it's like choosing the right tool for the job? What are some of the factors we need to consider when making this decision?
For example, using an aesthetic score verifier might be great for generating visually stunning images, but it could lead to the model overfitting to style at the expense of content accuracy. In some cases, we might prioritize accuracy over pure aesthetic appeal.
That makes sense. It's like a painter focusing so much on brushstrokes that they forget to accurately depict the subject matter. Are there any specific examples from the research that highlight the importance of choosing the right verifier?
The researchers tested different verifiers on Drawbench, which uses general-purpose prompts, and T2I Combench, which focuses on more compositional prompts. The results showed a significant difference in performance, depending on the verifier used, underscoring the need for careful selection.
So it's not just about picking the fanciest verifier. It's about understanding the nuances of the task and choosing the tool that aligns best with our goals. But here's something I've been wondering. What if we're already working with a diffusion model that's been fine-tuned to align with human preferences? Can we still benefit from this noise search technique? Or is that only useful for improving base models?
That's a great question, and the research actually addressed this directly. They used a technique called Diffusion DPO to fine-tune a stable diffusion XL model, aligning it with human preferences. Then they tested whether noise search could still improve its performance.
So they essentially took an already high-performing model and tried to make it even better. What were the results?
Surprisingly, even with this fine-tuned model, noise search still led to noticeable improvements. It shows that this technique isn't limited to improving base models. It can enhance the performance of even highly optimized models.
That's pretty amazing. It's like finding a hidden upgrade for a device that you thought was already running at peak performance. So now that we've seen how powerful this technique can be, let's talk about the practical side of things. How do we go about allocating our computational resources during inference to get the most out of this noise search process?
That's a crucial aspect. There are several factors we can adjust to fine-tune the performance. One is the number of search iterations. More iterations generally lead to better results, but also require more computational power.
So it's a classic trade-off between quality and computational cost. What are some of the other knobs we can adjust during inference?
We can also adjust the compute allocated. To each search iteration, investing more compute per iteration can yield better results. But there's a point of diminishing returns.
It sounds like finding the sweet spot is key. Are there any other considerations when it comes to allocating resources?
The final consideration is the compute allocated to the final generation of the image. We always want to use the optimal settings for this step to ensure the final output is as good as it can be.
So we're strategically allocating compute throughout the entire process, from the initial noise search to the final image generation. But this brings up another question. What about smaller diffusion models? Can this noise search technique help them compete with larger, more resource-intensive models?
That's an intriguing question, and the research offers some encouraging answers. They compared 3 different sizes of a model called SIP-TT on ImageNet: SIPB, SITL, and SITXL.
So we have a small, a medium, and a large model. What happened when they applied noise search to these different sizes?
The results were fascinating. Smaller models, when combined with noise search, were able to achieve performance comparable to, or even better than larger models, without noise search.
So we can actually use this technique to level the playing field and give smaller models a competitive edge. That's a game changer. It opens up so many possibilities for researchers and developers who might not have access to massive computing resources.
Absolutely. And this finding extends to the text-to-image domain as well. They compared a smaller model, PixArt-A, with a larger model, FLUX Sadotset Dev. With noise search, the smaller model was able to achieve significant efficiency gains, demonstrating that this technique can bridge the performance gap between models of different sizes.
This is really exciting. It seems like noise search has the potential to democratize access to high-quality image generation, making it possible for a wider range of people to participate in this field. But before we get too carried away, let's take a moment to reflect on what we've learned so far.
I think the key takeaway is that we've discovered a new frontier for scaling AI performance. Traditionally, the focus has been on scaling models during training, building bigger and more complex architectures. But this research shows that we can achieve significant gains by strategically allocating compute resources during inference.
So we're shifting our perspective from building bigger models to making smarter use of the models we already have. That's a pretty profound shift in thinking.
Exactly. And this has some really interesting implications, especially in terms of making these advanced capabilities more accessible. Smaller research groups or individuals who might not have the resources to train massive models can still achieve state-of-the-art results by leveraging inference time scaling techniques.
That's a really exciting prospect. It levels the playing field and opens up the world of cutting-edge AI to a much broader audience. But stepping back for a moment, this whole idea of finding better noises seems almost too simple. If we can unlock so much potential by being more deliberate about our starting point, what other hidden gems might we uncover within the diffusion model generation process?
That's the big question, isn't it? This research really just scratches the surface of what's possible. There's so much more we can explore in terms of noise selection, verifier design, and algorithm development. The possibilities are truly vast.
It's almost like we've stumbled upon a secret passageway, leading to a whole new world of possibilities within diffusion models.
And who knows what amazing creations await us as we venture further down this path, the future of image generation. With diffusion models, it's incredibly bright, and I can't wait to see what the next breakthroughs will be.
Well, listeners, our deep dive into inference time scaling has come to an end. We've journeyed from theoretical thought experiments to practical implementation details, uncovering the incredible potential of this emerging field. But the exploration doesn't end here. We encourage you to continue learning, questioning, and pushing the boundaries of what's possible with AI. Who knows, you might just discover the next groundbreaking technique that revolutionizes the world of image generation. Until next time, happy exploring.